All right, taking a look at AP Physics vertical motion. Okay, but now we are on to problem number 4. Okay, problem 4 says a ball rolls off a table with horizontal velocity Vx. All right, and it says on a diagram below, sketch the possible trajectory from the table edge to the floor. And so you say, okay, if I've got a table, and you say, okay, here is my table edge, right? And the floor. And you say, okay, one possible trajectory for this ball might be something like this. I might say, dude, it's rolling along and it rolls off that table edge. And so it's going to be going at a constant speed sideways because there's no forces sideways to push it faster or slower. But vertically, it's got an unbalanced force because of gravity pulling it down, accelerating it downward. So it's going to go faster and faster and faster down while it goes constant speed sideways. So every second, it's got to go farther and farther vertically while it goes the same amount sideways. And that's going to bend it into a curve. And so I'm going to get this parabolic path, something like that. Right? So then we go ahead and say part B. Now on the same diagram, sketch 2 other trajectories. Okay, one for a value of Vx that's smaller than before, and one for a larger value of Vx. And then draw a 4th trajectory for an extremely large value of Vx and label them. And so we say, okay, this was Vx there, right? That initial horizontal velocity. But I'm going to go ahead and draw a few more. So maybe one that's going a little bit slower. We'll say, so if my Vx is shorter, then this guy, it's going to have the same vertical motion. It's just its horizontal motion is slower. So it's as if I took this curve and I just scrunched it down sideways. Right? And so this is slower. Okay. And if my Vx was faster, then starting the same spot, now my Vx is faster. And so it's going to be going same one, but now I'm just grabbing that curve and stretching it to the right. The vertical motion is identical. It's just the horizontal is getting changed. So again, I'm starting, right? Again, I need to have a horizontal tangent at the start, okay, for all 3 of these, right? And in fact, all 4. Now we need one that's going like really honking fast, right? And if it's going really, really fast to start, right, with some like really huge V in the X, then you say, this one is just going to be like, shoo, right? Okay, you're not even necessarily going to see it hit the ground. It's going to go off the edge of the page, right? Okay, it will eventually hit the ground though. In fact, it's going to hit the ground in the same amount of time that it took for these to hit the ground, right? The vertical motion is identical. It takes the amount of time to reach the ground. It's like the vertical motion kind of determines the time, right? Okay, anyway, so moving onward. Then it says, part C. We say, oh, I'm supposed to label all of them, right? So we had slower. This is going to be faster. Ever tell you that my brother-in-law and sister-in-law, they had a dog named Faster? He used to be like a greyhound, like a racing greyhound. That was a rescue. Anyway, really, really dumb dog. And this is like fastest, right? Okay. Alrighty, here we go. Now it says, we say the shape of these trajectories is parabolic for the ideal case where air resistance is negligible. What is a parabola? How do you know that these are parabolic? So you say, well, we remember that a parabola, right? You might remember from like, math classes and such. The parabolas basically have like a, y is proportional to x squared, or x is proportional to y squared sort of a graph, right? That's the sort of thing that we're looking for here, right? So it's a relationship between the vertical position and the horizontal position. That's the shape, the trajectory. Notice that time isn't in there, because what I want is a relationship between the x and y position, that the path right? X and Y coordinates give me a parabola, okay? And that's key. I want an equation that's got X and Y. So what I'm going to do is I'm going to write an equation for a problem like this. We're taking off horizontally. Let's take a look at each axis individually. If I look at the horizontal axis, then aren't I going at a constant speed? So wouldn't I just say, like, if we go ahead and call the initial position 0, sound good? Then it's like delta x is v naught t plus 1/2 at squared. You say, well, gosh, in the horizontal axis, there is no acceleration. My a in the x is 0. And you say in this delta x, if I just call, I'm just going to choose to call, is it okay if I call the initial position 0, 0? Thanks. So if this initial position is 0, 0, then this is going to be like, x minus x naught, but x naught is 0. So I'm just going to get x is that initial, and now this is just the horizontal velocity. You know what I mean? Should I just call it Vx? Vx naught? V naught in the x? I guess I'll call it V naught in the x. There we go. V naught in the x times t. Now we go to the y-axis. And you say, in the vertical axis, we can use the same formula if we wish, because we want to get something with position, right? Because we want the y position. I'm going to write it as delta y instead of delta x, if that's okay with you. And it would be like, v naught in the y t plus 1/2 my acceleration in the y. Acceleration in the y, isn't that going to be like negative g? Sure. T squared. And you say, hey, you know what v naught in the y was? For this case, they take off horizontally. What was the vertical speed at the start? Isn't the starting speed in the y 0? So this whole term is going to drop because that's 0. And if we call the initial position 0, 0, then this, delta y, that's like y minus y naught, but y naught is 0. So what I'm going to get is that y is negative g over 2 t squared. Okay? Looking simpler already. And so what I want is an equation for like y as a function of x. So I want to get rid of this t business. So what I'm going to do is I'm just take this equation and say t is x over v naught x. And then I'll take this, right? And I'll substitute it in for t to get rid of that t variable over here, right? And if I do that, then I'm going to get y is negative g over 2. And then I'll have that v naught x is going to get squared, right, in the denominator there. And then I'll have x squared. And look at this. Do you see this? That's a constant. V naught in the x, that's starting horizontal speed. That was a given. In fact, V naught x, that's just what they called Vx, right? So I probably ought to get rid of that x. So it's the same notation as in the previous part of the problem. So I'm getting like negative g over 2 Vx squared, because it's a constant velocity in the x anyway. I don't need the naught because it's constant speed in the x. X squared. Right? And you say, hey, I recognize, again, constant times x squared, y is proportional to x squared. You say, hey, that's an equation for a parabola. Hot diggity, it's a downward opening parabola. That's our equation, QED, right? What we're supposed to demonstrate. Quo errata demonstrator. So then we're all set. And so this is why we say that a projectile, ideal projectile, no air resistance, follows a parabolic path, because it does. Ignoring curvature of the Earth and all that. Assuming a uniform gravitational field and all that business. Okay, which brings us to, let's see here. Yep. Now it says, part D, what would the trajectory be like for a ball with the same initial velocity but twice the mass? And you say, ignoring air resistance, it would be the same. Did we use mass in any of these calculations? No. The only equation we're going to use mass is like, if we do sigma F is ma, right? But the thing is that gravitational force is the only force acting. But isn't it true gravitational force is just m times g, and it's equal to m times that acceleration? And you say, isn't it true the mass just drops out? And so all objects have that same vertical acceleration, negative g, going down, right? Yep. That's the case. And so, the mass does not matter. And that is problem number 4.